You know.
Right. You don't know.
Quick announcements before we get started. What is happening in this class? We have a lab due tonight, we have a project due on Friday, and we have a final on Monday. Study guide is uploaded, so people can take a look at that if you'd like to. Has anyone who's had a chance to look at that have any questions ahead of our study session on Friday? I will continue to ask at the start of each class period if I can clarify anything on the final study guide ahead of Friday's full study session so that you can come prepared for that.
So, since this is like a lot of the same stuff from earlier, can we do some like little arts and crafts and like cut out stuff so we don't have to rewrite it? Or what?
In what sense?
That's good. You photo scan and shrink.
Yeah.
And then it's so small, I won't be able to see it.
So the plan for today is to finish up adapter and facade and start our whirlwind tour of all of the other design patterns that we didn't have a chance to cover. Then the remaining couple of days before Friday, we're going to have some kind of application day where we do something applied. It could be another problem. It could be something related to implementing a design pattern to something. I haven't fully figured out exactly what I want to do yet. And then I assume that we'll also have one project work day. Would it be more useful to have that project work day tomorrow or Thursday for anyone who cares?
Thursday.
Hands for tomorrow?
Yeah.
That's a good point back there.
Hands for Thursday?
I don't really care, honestly.
Oh, that's tough.
That's serious.
So it looks like we have a slight preference for tomorrow. So I think that would help people get prepared for that. So I'm gonna say tomorrow is our work day. I think that does give people a little bit more time to iterate on that feedback and get it working by Friday as well. I will continue to have office hours throughout the week as well, so please feel free to come talk to me about any individual stuff. But yeah, tomorrow we will have a work day, and Thursday, I guess we can decide tomorrow how to best utilize Thursday, but I'd like to have some kind of either OO-based practice problem or something of the sort prepared. Questions on the remaining schedule for just the few days of class we have left?
Are you gonna be in your office after class?
Yeah. All right. So last time we talked about the facade pattern. So we decided that if we were using this 90s home theater system, there were a lot of steps involved to preparing for a party. So we wanted to abstract that so that the client didn't have to do all of these steps. We could instead introduce a home theater facade where the facade takes each one of the components of this system as an input. And then we can define a bunch of methods in the facade class that do complicated tasks. So that way the client only has to specify one of these methods, and then lots of the components, we interact with all of the components of the system through the facade. And that simplifies everything from the client's perspective, even though it blows up the complexity of all of our classes. And we add that facade to everything, but it allows us to do something like the watch movie method that interacts with all of the components of the system. The end movie method, which interacts with all of the components of the system. Then we can find that, again, from the client's perspective, the now home theater driver on the left here is very short, and we get a lot of output here on the right because it's been abstracted into the facade class rather than the client's responsibility. Any questions on our recap before we head into the last couple of slides? There's not too much to do left here. All right, so the facade pattern as a whole just gives you a single interface to connect to a subsystem. So now the client only has to interact with this facade interface and not the complicated subsystem. We talked about the principle of least knowledge. That was the last thing we talked about in the last class, so only talk to your immediate friends. When we're designing a system, we want to minimize the number of classes that each component interacts with. And we want to minimize interacting with things that are very far removed from that component in the entirety of the system. If we have lots of dependencies between classes, the system itself is very fragile. We make one small change, and maybe that change has a bug in it, and it can break a significant number of pieces in that subsystem. If we have a facade now, then it is much better. And also becomes costly to maintain, because if the client wants to make any changes, then there are lots of different connections that we have to worry about in the subsystem and not just the immediate neighbors. We have to look at the entire web of the system. It also becomes complicated for others to understand. In general, the design philosophy is we have an object, we only want to call methods that belong to the object itself. So our own behavior, great. Objects passed in as parameters. If we are going to use that object, then we should be passing it in as a parameter. We shouldn't be accessing an object that we don't pass in as a parameter as part of a particular method. So an object that this method creates or instantiates, if we actually make an object in a method, we can use that object's methods or components of the object. If this object has other classes that are components of that object, then we can communicate freely with those. But this just keeps everything close at hand to what is immediately being cared about. The object, things that we pass in as parameters, any object that we create inside of the method, and any related components of the object. If you're interacting with things outside of the scope of that, you're violating the principle of least knowledge. And with all OO principles, you cannot adhere to this all of the time. It's just a design philosophy of, if you can, it's likely going to be better for you to adhere to this principle. It will make things easier to maintain and less complicated. We'll give you an example here of a car class. A car class has a component, the engine. So because a car contains an engine, the engine methods are free to be accessed because there is a component of this class that is that. So in the start method, we create an object doors. So it's perfectly okay to call any methods that relate to doors because we instantiated that within the start. So this gives you a very good idea of update dashboard display, for instance, is a method that is part of the car class. So we can call that within the car class. And this adheres to that principle of least knowledge. We don't want to randomly call some other object outside of the scope of that. Questions on this example? Last example is the home theater example. So now the client only has one friend that is the facade. So the client should not be accessing anything that it's not directly able to create, because the client will instantiate the home theater facade. The client is not instantiating the tuner or the amplifier or the DVD player, so the client shouldn't be accessing its methods. The facade should be implementing those things so it can freely access those. Questions on this example? All right, well, this is the end of adapter and facade. So there is one more survey that I'd like people to take just for the data and information, so I'm quickly going to reveal that survey so that you all can take it. Is up. So it should be the same questions as before, but I just am curious how people feel about adapter and facade, given the lecture style. So please fill that out. I'll give people a little bit of time and I will get ready for the whirlwind tour of the rest of the design patterns. Who's still working on the survey? Few people, a few minutes. Phil, answer who's still working? All right. So we've gone through all of the creational patterns in this class, which is nice. There are no new ones to go over. The creational patterns are meant for discussing how objects are created, as well as giving some additional functionality to the creation of objects that might save us some time, be more extendable, be able to utilize more complicated patterns or more complicated structures. So we've gone through all of these. We should know them at a basic level by now. So what's left is some of the structural and behavioral patterns. So going through these structural patterns, we have now covered adapter. We've covered bridge. We have not covered composite. So let's talk about the composite structure. So you see the word composite, you can think of composition, and you can think of composing objects out of other objects. This is very useful if you have a complicated composition structure in your requirements. So you can think of composition as a big tree where you have a big box, and inside that big box there are smaller boxes, and inside of those boxes there are more boxes, and eventually inside of those boxes there are items that you care about. So only apply this if the model can be represented as a tree. So if you have a way of structuring the composition as some kind of tree, then you want to apply the composite pattern. You can think of something like boxing up a very complicated Amazon order, where we have an order for a hammer, a phone, headphones, and a charger. Very strange order, but the idea is that we don't want to box the hammer with the phone because the hammer could damage the phone if it's in the same box. So we need some kind of tree structure to box up the phone and headphones, another box for the charger, put those inside of the same box because they all have to do with the phone and related accessories. Then the hammer goes in its own box. Those boxes and a receipt object all go inside the large box that then gets delivered to your door.
Do we need to know about these while they're rushing through?
No, so for this, these will not show up on the exam.
Okay, these are just know about it. Just-
Yeah, this is just in case you see these situations in the future, you'll know that these design patterns exist.
Why would we stick all of the boxes in the boxes? Like, you put the hair box out the floor box, your probate is not gonna do so well.
Yeah, well, we want related things to be put together, basically. So here we're breaking down the complex order into smaller orders, smaller boxes that contain smaller boxes, etc. So the direct approach from this complex order is to do something that looks kind of like a depth first search, where you take out all of the boxes, go over all of the products, and then you could do something like calculate the total of the order, the total cost of the order. But the solution is going to basically be the composite pattern. You can have products and boxes through a single interface. And then there's a method in that interface for calculating the total price or the total of something in that hierarchy. So you can think of this also as something like military structure, because that can be done in a tree form where you could do some kind of depth first search to find this. So the great thing is that we're abstracting the calculation of the price outside of the individual objects and instead have some interface that keeps track of the logic of boxes that contain items and items at different levels in the hierarchy. It allows us to interact both with boxes and with objects inside of the same inheritance hierarchy. So here is the UML for it. The client interacts with components, the component interface, and then there is a component array inside of the composite that keeps track of all of the items that are in this case, that shipment. We can add things, remove things, and since it's in a tree form, we can get the children for any one of the items, which can either be additional boxes or additional items. And then we have an execute function in both the composite, where we know that's not a leaf, and a leaf that does not have any children. So we can use this logic combined to get the associated price of the entire order through the same interface. Questions on composites? That's basically the extent to which I want to go over it. This is kind of, again, going to be a whirlwind tour of everything we haven't seen. Just for your knowledge. Next one is flyweight. Flyweight is a very memory-related object or very memory-related design pattern. So we want to be able to store more objects in the same amount of RAM by doing things like if this item shares something with this item, then we can overlap and store them in one place where they have two different accesses that does this. So it's a structural pattern to do that. So the problem is fun. We decided to create a simple video game. We're going to move around the map and shoot each other. If we implement some kind of particle system, the idea is that we need to instantiate and create new particles for every single particle that's on the screen. So we end up with a significant RAM cost to keep track of the location and velocity of each one of these projectiles in the three-dimensional space that is the game world. So it was running flawlessly on your machine, but your friend wasn't able to play for as long because they don't have as much RAM. You discovered the game crashed because of an insufficient amount of RAM. So your particle system, each bullet was represented as a separate object containing its own data. So we see that the RAM cost of a particle is it stores the coordinates, a vector of the direction that it's headed in, its speed, the color, and some kind of actual sprite. The sprite being the artwork of the bullet. So we find that each bullet takes 21 kilobytes, and there are 1 million bullets flying around the screen at a time. So that takes 21 gigabytes of RAM to display all of those bullets on the screen at the same time. Who has 21 gigabytes sitting around in their computer that they can use for bullets?
If you have like a super beefy PC, maybe. Yeah.
I would at home. I have 64 gigs of RAM. It wouldn't be too bad to apply 21 gigs of RAM to this. But I do that, test it, it works fine. I hand it to someone who does not have that level of RAM. What looked fine and bug-free on my system looks very buggy or causes crashes on somebody else's machine. So we want to be designing, thinking about what is the lowest level of performance that I want to be able to support. Do I actually go through the math to figure out when all of these projectiles are flying around the screen? Is it going to work on the target machines? What are the minimum specifications I want to state for the game that I'm making? So you look at the particle class and you notice that all of our bullets share the same color and the same sprite. So the idea is that we don't need to instantiate separate colors and separate sprites for each bullet. We can just copy one existing color and sprite, and that way we don't need to instantiate 1 million colors and sprites. We make them static and refer to the same object. So we can now make a moving particle class. We can take this where we no longer store the sprite that exists in a particle, and if the particle is moving, then we get rid of the sprite for that. So the immutable state of the particle is the color and the sprite, and the mutable state is the particle coordinates, vector, and speed. So that means that we don't have very many of the immutable objects, and we have lots of the mutable objects. So we see that when we do this, by only creating a few of the color and sprites, we have a total of 21 kilobytes. There's one of those, and there's 1 million of the 32 bytes. And now we have reduced our memory requirement from 21 gigabytes to 32 megabytes. Who in here could run 32 megabytes worth of RAM in a particle system? No? What decade are you in? Everyone can run 32 megabytes worth of.
Not this thing.
I mean, only if it's a Chromebook. If it's a Chromebook, maybe not. I just have a personal vendetta against Chromebooks. So the idea is that we're going to break this out into mutable and immutable parts, create a flyweight between them. And now we can, basically you're utilizing the concept of static, where when we need the color of a particle, then we go get it from its static representation rather than making a new one each time. We see them paired with factories very frequently. So you can create a factory that manages a bunch of existing flyweight objects. So again, you can design lots of design patterns together in ways that help you to create complex subsystems that do that. Questions about flyweight? All right, let's talk proxy. So proxy gives us a way to substitute or give us a placeholder for some other object. The proxy is going to give us a way to access the original object. That way we can do something before or after the request goes through the original object. So here we have a bunch of clients querying a database at the same time. So we have a large object consuming a large amount of system resources. We need that from time to time, but not all the time. The idea of a database query being very slow, if we have a complex database query, it can take some time to get that associated information. So the lazy initialization says that we're going to create the object only when we actually need it. So whenever a client needs access to it, we defer the initialization. As we do this, we find that we need to duplicate that code across every client that needs access to that database. So the solution is to put a proxy in the middle of all of those client requests and the database. So the proxy looks like a database object, so the clients can connect to it. The proxy then adds additional logic that says when the database queries happen, such that we don't have that level of performance overhead. The proxy is just a storage structure for client requests. So the proxy needs to, when it receives something from the client, create the service object that is going to interface with the database and delegate the work to that process that communicates with the database, gets back the result, and communicates that result to the client. So here's an example. We have a payment interface that can either take a credit card payment or a cash payment. Note that the credit card is a physical object that controls access to your bank account. So it's a proxy to your bank account. And the bank account, of course, is a proxy to cash. So both have the same interface. They can all be used for making a payment. There's no need to carry lots of cash around. You can just carry your credit card around, and it is the proxy for paying with cash. So we have a proxy, we have a service, and we have an interface for that service, and the proxy is going to perform that service via some other method. Preferably something that makes it easier on the client so that they don't have to carry around cash. Questions on the proxy pattern? So these are all of these structural patterns. Those are the three that we didn't really get around to. There are lots in behavioral that we didn't touch on. So we need to touch on chain of responsibility. We talked about iterator in 300, but we'll talk about it a little bit in here. Mediator, memento. Memento is actually really important for 350. State, template, and visitor. So quite a few behavioral ones to cover. I don't think we'll quite get to all of them today, but let's start with chain of responsibility. So this is the equivalent in computer science of the elementary school game of telephone, where we have something that is a long request chain. We go from A to B to C to D to E to F that handles it back to E to, I'm not very good with the backwards alphabet, but we have this big long chain. And you can think of it, the example that they give you is an online ordering system. We want to restrict access, so only if you are authenticated can you actually create an order. So we want to give administrative permissions to all orders, but we realize that the request has to go through a large authentication and authorization procedure that either accepts or rejects the problem. So we find a way that you can create a large chain of responsibility in here. So we have a bunch of sequential checks. So we don't want to pass raw data straight to the ordering system. We need an extra step to make sure that the data is actually in the request. Then there's a brute force password cracking vulnerability that we find. So we need a check that filters for repeated failed requests coming from the same IP address so that they can't brute force crack somebody's password. We could speed up the system by returning cached results rather than looking for repeated results over and over and over again. If it's something that they looked up recently, we can cache it, and that way they can look it up again faster the second time. So we need another check to figure out, is it in the cached system, yes or no? So this becomes a very complicated authentication, authorization, validation, caching system that is in between the request and the ordering system. So we could probably benefit from some optimizations of this structure in order to access the ordering system a bit faster. So now we have handlers where each individual handler can fail along the way to the ordering system, rather than having a bunch of concrete logic that either results in success or failure. So we can discretize this process and say that each handler now can run as long as the previous handler said yes, rather than just this big long chunk of somewhere in here we rejected, or after all of this we accept. We have a bunch of different processes that are each responsible for an individual check in this system. So here's an example of a chain of responsibility and a much more complicated. So we have windows that contain panels and toolbars, panels contain subpanels, subpanels contain buttons. So we have a big object tree. When a button is pushed, we want to go to the subpanel, to the panel, to the window to do something to go back to it. So we can create a chain of responsibility inside of an object tree to be able to do something like this. So tech support would be another example of a chain of responsibility where the only time the manager handles an issue in tech support is if they have tried turning it off and on again, and that wasn't the issue. So there are a lot of people who can diagnose turning it off and on again. So we handle all of the requests through someone who can handle the most basic and filter it through the most basic chain. But to move up the chain, they need to have failed at what they're doing, which allows you to access the manager. So chain of responsibility, we have a handler interface. The client goes through the handler interface that figures out where to direct their response. Then we have a base handler and concrete handlers that we can then pass along the associated chain. So that is the chain of responsibility pattern. Questions on that? I know this is truly thrilling stuff, isn't it? We talked about command. We know iterator a bit from 300, so this is just for traversing elements of collections. So we have lots of different types of collections. Here we might have a linked list. Here we might have a graphs adjacency matrix. Here we might have a tree structure. So there are lots of different kinds of collections. We want the ability to iterate through and add and remove during that. So we just specify some way of traversing a particular collection of objects. If we have a traversal for that collection, then we have a way to access the next element in that collection. So it's just something that we need to specify to make an iterator is how do we access the next element? So here we have a depth first iterator and a breadth first iterator over a particular tree collection. We can determine what the next element is that we can use to traverse that collection as long as we define what that is. How are we determining the next element? So that's the iterator. Mediator. This helps us if we have a bunch of dependencies in our objects. We want to reduce the number of dependencies between those objects. So this pattern will kind of create this traffic helping object that will redirect communication between objects, and any collaborations that happen between those objects have to go through the mediator in order to be able to communicate with each other. So here we have a very complicated interaction between a bunch of objects that all need access to each other. Instead, basically, we can make a mediator that is the associated dialogue, and now everything goes through the mediator to be able to connect to each other. So a button can connect to tabs, a checkbox can connect to a text field, but all of those go through this dialogue class that is mediating all of that communication. So it reduces these chaotic dependencies that we have here. And that way, if changes are made, then we can always access those changes through that mediator object. So here is air traffic control being the mediator of a bunch of planes trying to take off and land all at the same time. There's communication that goes through the mediator creates the plan for how something happens in real time based off of those requests. So perfect example of a mediator in the real world. So you end up with components, a mediator interface, all of the components communicate with the mediator, and the mediator notifies the other objects of each other's communication as it is relevant. We don't want every plane talking to every other plane when they're trying to take off and land. We need some mediator that says, yes, you can take off. No, you cannot take off. Wait for a moment. You don't have to figure that out yourself through the chaos of talking to every other pilot of every other airplane. Questions on mediator? This one's really important for the project that most of you will do in 350. It's called Memento. The issue is that we want a history of an object. We want to be able to restore previous state. So this is used most frequently for lots of undoing and lots of redoing. We want to be able to store undos and redos, and we want to encapsulate those so that it's the object itself creating those snapshots. We don't want an outside user to be able to create that associated snapshot. So for instance, let's say you want a transcript sent to a potential graduate institution. Should you have the ability to create your own transcript? That seems like a really bad idea. You want to communicate to the institution and say, send my transcript to that institution. That way, when the institution receives that, they know that it was the institution that created it. You didn't get your dirty 4.0 fudging paws all over your own transcript to make yourself look better. Because if everybody could do that, then we would never be able to take transcripts seriously. So the memento just makes sure that it's the object that should be creating the snapshot that's creating the snapshot of something like your academic history. So here we have some kind of history. In the editor, we want to undo to be able to grab that history. But the history should be produced by the object itself, not by an outside. So the editor has a bunch of private fields that we should not be able to access, let alone copy. So if we have public access to it, then it's unsafe. So that means that the editor needs to be making its own snapshots. So to adhere to memento, you're going to be taking an object, creating a class basically that allows you, basically you're going to be taking this memento. The memento itself is what's storing these snapshots, but the editor itself can make snapshots and restore snapshots that are passed in from the memento. That way, the originator, this editor, is producing the snapshots. The memento saves those snapshots. And then the history that we care about, if the user wants to recreate something from that, these aren't editable. Like the editor, you can change the memento, but changing the memento doesn't change the original object. So it's the idea of an unofficial transcript. If I hand you an unofficial transcript, the reason that it's unofficial is you have access to it. It's not coming directly from the institution. But it might be a history if you got an unofficial transcript at the end of each quarter that you were enrolled, you would have a history that you could then go refresh. If there was some way to do something like, I'd like to undo this quarter, if this quarter just wasn't kind to me and I'd like to be able to go back in time, then you could do that because you had a snapshot of what your transcript looked like at the end of last quarter. So you could feed that snapshot if the university were storing that back into the system to undo or redo any number of quarters and history of the object. Because it is the originator that's making the memento and using the memento. Does that make sense as to how that does kind of an undo redo philosophy? So we get this concept of a caretaker that's going to store the history for us. So the originator would be the registrar's office in this case. The caretaker would be some Eastern database that records and registration stores that history in. And then you could make a query to that system that says, hey, I'd like to undo the last quarter. And then they could go access the database, the caretaker, for where that was stored and then restore that in the original object. And during none of that process did you have access to your own transcripts. So you get finally something that looks like this. An originator interface, concrete originators, a memento interface, concrete mementos that have the history basically, and then a caretaker that stores that history. So each concrete memento is stored in the caretaker's memory, which then can undo, and the concrete memento can restore. So you get undo and redo from the concept of this object. So we have state and template and visitor. I guess we can try to get through state. Questions on memento before we move on to state? All right, so we want to now alter behavior on an internal state change. What happens is it looks like from the outside, an object has morphed into another object. Instead, all we have is a trigger that says, when something happens, change my internal state to look like something else. So, finite state machines, you'll see these in compilers, if you take compilers from me. Basically, this is a fun kind of graph where each vertex represents the internal state of a system. And each edge represents something that you can do to transition from that state to another state. And these can represent complex ideas or complex systems. So each node represents a state, and each edge represents changing that state from one to another based on something. So that's a finite state machine. So each program can be in a finite number of states. Within each state, the program is going to behave differently. And so we can switch from one state to another by doing something. Here's an example. You're writing a paper. So you write a draft, you publish the draft, it goes into moderation. If your editor says this is garbage, then it goes back to the draft form and you have to rework the draft before you pass it back to your editor. Once you do, you pass moderation. Once it passes moderation, then it's actually published. Once it's published, maybe the publication expires and you have to go recreate it. So here are the different states, draft, moderation, and published, of some kind of document. Here are the transitions representing what happens to that object to transition between those states. Usually we do this with a bunch of if or switches, which is really gross. So publish, we can publish from a draft state or a moderation state or a published state. And then this creates a big long block of logic. So instead, you can make a state object where we now can have a draft that inherits from that interface, and then we can render and publish from any state that the draft could be in. By every one of those has their own render and publish methods for what is the logic for publishing from this particular state. So that's what the state pattern is trying to accomplish. Buttons and switches in your smartphone behave differently depending on the current state of the device. When the phone is unlocked, pressing the power button turns it off. When the phone is locked, the power button turns it on but doesn't unlock it. When the phone's charge is low, pressing any button will now show the charging screen instead to say that you need to charge your phone instead of displaying something like it normally would. So this is an example of a state where we could now basically say, whatever state we happen to be in, here is the logic for how to handle this button press, given that we're in that state. And it's a way of just abstracting all of that logic down into each of the concrete state classes, rather than trying to have one big long, if we're in this state, then do that. Else, if we're in that state, then do that. Else, if we're in the other state, then do this other thing. So we reduce the long if or conditional block down into a set of state objects. We'll cover the last two at the start of probably tomorrow's class period. And then we'll have the rest of the class period available to work. So I will see you tomorrow for that. I will be in my office if you have any questions about the project or the lab that's due tonight.